you very much, Philip. And of course, thank you for the invitation to give this talk and to the program. The goal of this paper is to bring together the study of combinatorial tameness properties of first-order structures in statistical modeling and Shelah, or we call neostability, and the study of geometric tameness properties of expansions of the real line championed by Miller. So this, Philip might have recognized, is the first sentence of a 2018 paper by him and Eric Waldberg. And the reason I'm including it is because I think it's a good summary of what I'm going to be talking about. So the whole idea of this talk is we're going to assume some combinatorial constraints on structures over the reals, and from this we want to extract some topological control, some topological tameness. Okay? But before we get to that, I do want to speak a little bit about sort of the big picture here. So this is a section of this universe of theories, right, that we really like in model theory. So every red point is a theory. We have these dividing lines, which are mostly combinatorial in nature, right? This pink section there would be the minimal theories. And this program of Miller that Philip and Eric talk about, what it does, it focuses on the reals. So that red point would be the real field. And in general, so quite often the way this program works is you consider the reals expanded by certain sets, like Cantor set. And what they're interested in is in the generated structure. You want to know if the generated structure, if the final sets are Borel, if the final functions are generically continuous in some sense, if they are generically differentiable. But it's more or less restricted to the reals, and in general this program has not cared so much about these dividing lines of model theory. And I would argue that this started to change some 10 years ago. So we have, for example, the paper that I quoted before, but we also have the work of Will Johnson. So that what Will Johnson does is he looks at all the minimal fields. Like he doesn't care specifically about the reals. He looks at all the minimal fields, and he shows that as long as they are not very simple, as long as they are not stringly minimal, then they have a definable topology, which he calls the canonical topology. And he shows that this topology is tame in a very precise sense, right? So this is a very nice result where, like, from combinatorial data, from this axiom of the p-minimality, suddenly topology appears, and it happens to be a nice tame topology. Okay?
You mean V topologies?
V topologies, yeah, exactly. And the basic axiom that gives it this tameness is that every definable unary set, if it's infinite, it has non-empty interior. This happens to be very, very strong. It's a clear generalization of minimality. So, people continue looking at these things, other classes like NIP, topological structures, and today I'm going to go all the way here to NTP2 theories. And we're going to focus mostly on structures over the reals. And again, the idea is we're going to assume NTP2 and see what we can extract from this. Okay, so when I talk about topological tameness, what do I mean here? A set is constructible, subset of the reals, if it is a finite Boolean combination of open or closed sets. So let's look at a few structures here.
Are you talking about the Euclidean topology, or are you talking about the Zariski topology?
Euclidean topology.
Okay, yeah.
Now, say that an expansion of the real line is constructible if every definable set is constructible. So, we have examples of minimal structures, they are constructible, and then you have this structure where you have the field of reals and you have a unary predicate for 2 to the set, so numbers also form 2 to the power of an integer, studied by Van den Dries in the 80s. It happens to be constructible too. But then we have these 2 examples. Now all of these examples are NTP2, they are NIP, by the work of Philip and other people. So, however, when it comes to 3 and 4, these are not constructible because we're adding a set in both cases that is dense and codense in R, and this kind of object is never constructible. So we cannot hope for constructibility, but what we can do is look at something called the open core. Now, given an expansion of the real line, the open core is the reduct in the language that contains a predicate for every non-empty definable open set in R.
What's a reduct?
So it's a subclass of all definable sets that themselves they form a structure. Right? So you have the field of reals, you take multiplication, then you have the reduct, which is just addition and the order. Right? So we talk about the reduct in the sense of definability because the language is changing completely, right? In fact, I should say some people, model theorists, they don't like this definition because it doesn't. It's not obvious how it depends on the theory, and in fact, it's not uniquely determined by the theory, but it depends on the structure, specific structure where you are. So some people might not like it that much, but I would argue that it makes a lot of sense, this definition. So first of all, if you're like in a algebraic language that you just have a bunch of operations and it's a topological structure, you want them to be continuous. So then all your primitive definable sets are closed, and you would be in the case of an open core, right? The structure itself would be its own open core, and this kind of idea, I think, I would argue, goes back all the way back to work of Robinson on topological model theory. He argues you're working with a topological structure, you want your basic predicates, once in your language, to be, in some sense, compatible with the topology. And this is exactly what we're kind of forcing with this definition of open core, right? Also, if you go back to the papers of Pillai, when they first published about minimality, then he was also publishing some stuff about generalizing minimality, and he asks precisely for this kind of property. He asks that every unary definable set is constructible. So again, this sort of definition has been floating around in the literature. However, it's not until the late 90s when this thing comes up. And what happens if we look at 3 and 4 and the open core, where in both cases the open core is minimum, right? In fact, in both cases, I think the open core is just the reduct where you take away Q and you take away the algebraic numbers. So we can hope for these NTP2 structures to have constructible open core, right? Okay, small note here, because of the language, open core is constructible means it's actually a quantifier elimination result.
Do we have any example of NIP expansion of reals whose open core is not minimal?
Yes, there's all of these that are NIP. So number 2 there.
But the open core is minimal. I mean.
Number 2 right there. So that's NIP, and it defines a discrete infinite set to the set. So it's not a minimal.
It's not.
It's a discrete set right there.
Open core is minimal.
In 3 and 4. But in number 2, so 2 to the set is a discrete set, is constructible. Every discrete set is constructible, so its open core is itself, and it's not a minimal. Mm-hmm. But it's an interesting question because, I will talk a bit more about this later. There is a question about whether every constructible structure is similar to 2 in the sense that every definable unary set is just an open set and finally many discrete sets. It's not clear where it is. I mean, I think the general idea is that it should exist something a bit more complex, but we don't have examples. All right. So now I'd like to spend some time. I'm telling you this is Tame, this idea of constructibility, but I haven't really argued why. So let me just spend some time to do this. First of all, an expansion of the real line by constructible sets is always going to define only sets in the projective hierarchy. So worst case scenario, we define everything, right? And that's what happens when you have field of reals and you add a unary predicate for the integers.
So this is remind me what the projective hierarchy is?
So this, how is this constructed? I mean, it's basically all Borel sets closed under projections and Boolean combinations. That would be enough.
Okay, that's exactly what it is. Okay.
I think so.
Yes.
Or is it?
Yes.
Okay. So it's exactly how a structure is constructed, right? Boolean combinations and projections. So for example, you start with all Borel sets, you would it would be obvious that you have the projective hierarchy.
Okay, so it's just a collection of definable sets in the language where where in the structure where you have all the Borel sets.
Yeah, yeah. So what's the problem with this? So Miller argues, the projective hierarchy is quite complicated. Many theoretic independence issues arise naturally in the study of its definable sets. For example, the statement that every real projective set is Lebesgue measurable is independent of set of C. Right? That is it's a sentence that I've seen in a few papers around this, just again arguing that it's not a very, you might argue, okay, all of them are definable sets in the projective hierarchy, this is pretty good, but it should be wasted. On the other hand, powerful tools from geometric measure theory can be used to analyze the definable sets in Borel expansions of R. So even if all the definable sets are Borel, this is already quite good. And of course, if everything is constructible, we're staying in the basic level of the Borel hierarchy, right? So it's the simplest case, let's say.
So what's the difference between the Borel hierarchy and the projective hierarchy?
Borel hierarchy is you start with constructible sets, and then you consider countable unions of constructible sets, and that's how you pass to the next level, and then complements of this, and then countable unions, and so on. So it's a way of constructing the Borel sigma algebra by steps, right?
I thought that's what you said, the projective hierarchy.
No, projective hierarchy is projections.
So in the Borel hierarchy, you don't allow projections. Is that what you're saying?
No, exactly.
Okay.
Yeah. In fact, this was the reason projective hierarchy and descriptive set theory started was because I think Lebesgue said projection of Borel is obviously Borel, and then 11 years later someone said no, this is not true, and then descriptive set theory. Okay, more things. So we have a.
Do you mean sigma 1? I mean, here, projective means phi 1, right? Because usually analytic sets are continuous image of Borel sets.
Yeah.
Not projective.
Analytic sets are in the projective hierarchy.
Analytic sets are not stable, are complement. If you close two courses, then you enter the projective set.
Yes.
All right, say we have a constructible expansion of the real ordered group. Again, more things about tameness. Something you might want is generic continuity, and we have that. So for every definable function f from x to y, there is a definable open dense set of x such that f is continuous on set. So this is pretty good. What else you might want? You might want a good notion of dimension and definable choice, and you also have these two things. So naive and topological dimension and real definable sets. By naive dimension, I mean the usual definition where is the largest k such that some projection of your set to some k coordinates has non-empty interior. And topological dimension, I just mean the usual Euclidean dimension. And again, R has definable choice. This works at least in this case where we are thinking about structures over the reals. It's just the definition of definable choice. We can choose a point along fibers in a definable sense. All right, so this is, I could say more about constructability, and there are certainly, I think, interesting questions, but I hope I more or less convinced you that this is a nice setting. And with that, let's move to NTP2. Well, first of all, happy carnival. Did I?
It's almost
a bit late. Okay, That's good. Slower rather than being too fast. Okay, NTP2. So what is this definition? It's kind of a shame Artem is not here today because he's the one that I would say started the systematic study of these structures, like in the paper 2014. The definition, as I mentioned before, is combinatorial, and it goes as follows. Structure is NTP2 if it does not have what's called the tree property of the second kind. And what is this? So R has the tree property of the second kind if there is an elementary extension n of R and some formula phi xy and parameters indexed by two natural numbers in the extension. and some k, such that first, if we fix the I, then this family of formulas here is k inconsistent. But then on the other hand, if we choose one j for every I, then this family of formulas is consistent. I should also say maybe in all the proofs I've worked with NTP2 ever, you can always assume that k is 2 inconsistent. I imagine there are cases where you need a bigger k. So the way to think about this generally is just you think about the matrix of formulas, right? And you're saying every row is k inconsistent, but then every sort of path down where you choose exactly one formula from every row, it has to be consistent. Okay. So with this, I think I can present the main result I want to talk about.
Could you go back to the definition again? I just want to, yeah. Okay, so. Okay. Thank you.
Okay.
What is meant by a partitioned formula?
So this might not be unary parameters, they might be tuples of parameters, and then we call one subset of the parameter of the fibra or also call it x, another one.
You've divided up the parameters into two.
Yeah.
Okay.
Okay. So what's the main theorem here? So let R be an NTP2 expansion of the real ordered group, then the open core is constructible. Okay, that's the main result here. And question here is, do we need to stay in R? And the answer is no, we don't. This works for the p-adics too, even in language without multiplication. And in general, what we do need is some form of compactness. So in fact, the theorem holds for any NTP2 expansion of a topological group, given a certain definable sigma compactness assumption. So you need sort of like in the reals you have an increasing definable family of compact walls, in the p-adics too, and you need this sort of compact behavior. We'll talk about this more later. Okay, so I'm going to spend most of what's left of the talk talking about how you prove this, but before that, I do want to mention a few additional results, mostly for the people that are familiar with the area. First, there is a strengthening of NTP2 called being strong. If you're strong, you have a better result. So if R is a strong expansion of the real ordered group, then the open core is d-minimal, which is this property, every definable subset of the reals is the union of an open set, finally many discrete sets. This was the example from before with 2 to the set, the d-minimal structure. Again, the idea is that there should be something that's not d-minimal, but it's still constructible, but we don't have examples.
And do you have an example of a expansion of all the groups or the reals, which is really NTP2? I mean, not an IP.
Yes. I'm sure. So there's things called expansions by generic predicate, which is not an IP. They are NTP2 in the simplest sense. Is this over the reals too? Does this work over the reals? Generic predicate, I don't know if
No, it's NIP, I think. It's still NIP.
Generic predicate?
Yeah.
I think it's I'm thinking about a paper, but they work with ordered groups, and they explicitly say.
Oh yeah, if you add group, subgroup, probably, but not.
No, but a generic predicate, I can't remember the definition, I'm afraid. But it's not a subgroup. I'm sorry, I have to look at it, but I do think that we do have examples.
Strong mean? Oh,
Strong.
yeah, okay, same question.
What is strong expansion?
What is strong?
Yes, what is strong?
From the strong is if NIP is equivalent to strongly dependent. So okay, you know NTP2 is defined. You have the notion of an ICT pattern in NIP, right? Of a certain depth. In NTP2 you have the notion of imp pattern. So strong means not having an imp pattern of depth omega.
Could you explain that in more detail?
Sure thing. We don't have time because talk is quite short, so we have some time for this. So
dp rank is aleph 0 minus.
let me see. Let me try to explain this with maybe I can just use this actually.
Picture, yeah.
So yeah. So the thing is, imagine we consider that for every row, it's not the same formula. It's different formulas. Okay, but you still have the same rules of inconsistency and consistency. Okay, but it's a different formula every row. Then we would say there is an imp pattern of depth 4. Okay? So strong means not having an imp pattern of depth omega.
Wait, depth 4, you mean you only have 4 rows?
Yeah,
Oh, okay.
Yeah.
You need one formula for each row.
exactly. And I think, okay, so NTP2 would be equivalent to having what? Having some ordinal where you have a maximal imp pattern of that of length that ordinal. All right. So as I said, if it's strong, then you have this better result. That might be true in theory, although it seems unlikely for in the NTP2 case. And second thing is, I want to talk about the Shelah expansion. The Shelah expansion of a structure is the expansion by externally definable sets. Is everyone happy with externally definable sets? Or?
No.
Okay. So we have our M, or rather our R, and we're going to think about a set defined by a formula with parameters, but the parameters are going to be not in R, but in an elementary extension. And so we think about all the elements in R that satisfy the formula, right? So it's definable, but externally. Right? And this is a very important construction, the Shelah expansion in NIP structures, because it turns out the Shelah expansion is a structure itself. So all the externally definable sets, they are closed under projections, they form a structure. So what I wanted to mention here is, if R is an NIP constructible expansion of a topological group, then the Shelah expansion is still constructible. Having said that, I've been wondering this week actually whether there is any case over the reals of any constructible structure, or the reals where the Shelah expansion is not just itself, where it adds meaningful new sets. Okay. All right. So with that, I think we can move to the proof of theorem A. We need to talk about two things, a bit more about constructible sets, and then about something called definably F sigma sets. So, okay, a few easy definitions. Subset of a topological space is dense in another subset Y if it's dense, and it is co-dense if the complement is dense, right? And with this, we have this fact about constructible sets due to Miller. So X is going to be constructible if and only if the iterated frontier becomes the empty set in finally many steps. Okay? And this is really the way to think about constructible sets, I think. It has some important consequences. Well, first of all, it now becomes obvious that if X is dense and co-dense, then it's not constructible, right? Because then this process does not terminate, does not get to the empty set ever. So the examples I gave before, I mentioned Q and the real algebraic numbers are not constructible. Now it becomes pretty obvious that this is the case. But there is something else that you can extract from this that I haven't really seen in the literature, but it has been crucial, in particular to prove this theorem A. And I'm going to try and explain with some pictures I made in Microsoft Paint. I guess this is something I should be doing in the blackboard, but
Can I go back to the previous one? So maybe I'm not understanding. So,
Yeah.
so for, oh, never mind. Okay.
okay, so this is it. And the frontier is something outside, right? Obviously not Euclidean topology. And this is the closure, this is a closed set. So the second frontier has to stay inside this closed set. So it has to go back inside original set, right? But this is also a closed set right here. So the third frontier has to stay inside this closed set, so it has to go back inside the first one. Makes sense, right? And we can continue doing this, and if the set is not constructible, all these sets are non-empty. That's what the fact set. So if you're say you're in a saturated structure, omega 1 saturated, you can consider this type definable set. Right? It's going to be non-empty. And what's really interesting about this set is not only it's non-empty, but again, if your structure is saturated, your original set X is going to be dense and codense in this K. So let me just write that. Say N is an omega 1 saturated elementary extension of an expansion of the real line. If X is definable in N and not constructible, then X is dense and codense in this non-empty type definable set K. And this really is, I think it's very insightful. One of the reasons is that this notion of defining something that is dense and codense in something else is so central in Miller's program. So let me give you a few definitions here.
So when you say X is dense, you mean that means that X intersect K is dense?
Yeah.
Codense. Okay.
So let me give you a few definitions. An expansion of the real line is noiseless if there's no definable set X that is dense and codense in a non-empty open set. Okay, so Q, for example, would be noisy, right? Q is noise, and we don't want noise. The reason it's called noise is because it's visualized as something dense and codense as sort of like signal noise in a television. Let's say. So we don't want noise. We talk about noiseless expansions. Even better than noiseless would be strongly noiseless, which is there is no definable set that is dense and codense in another non-empty definable set. Okay? And now we realize by lemma B, it's constructible if there is no definable set which is dense and codense in a type definable set. Right? So you can construct this notion of constructibility in terms of objects that are dense and codense. In fact, these definitions are really very, very connected, and this theorem A actually came from another theorem that was proved in 2022 by Eric that says if R is an NAP expansion of the real ordered group, then the open core is strongly noiseless. Right? This is what we were discussing in fields, Philip and I, like in 2022, and thinking about how to, maybe streamline Eric's proof, and it's from this effort that came this theorem. But in fact, I think my point somehow, I'm trying to make also with this talk, is in many cases, in this whole area where people talk about strong noiselessness, it would make sense to talk about constructibility instead. The better property seems to make sense to consider it. And in fact, the proof I'm about to present is actually way simpler than Eric's proof of this theorem. Okay, so that's what I want to say about constructible sets. Second thing is the finally F sigma sets. So F sigma, it's from topology, right? F is for Fermat in French, sigma for sum. They are countable unions of closed sets in topology, and we want a definable version of this. So say that a family of sets curly C is upward directed if for every two sets in the family there's a third one that contains their union, and say that a definable set X is F sigma, definably F sigma, but I'm just going to say F sigma, okay? If there exists an upward directed definable family of closed sets such that its union is X. So we're changing countable union by definable upward directed family, right? We have similar definitions called D sigma in the literature, but this definition works for an arbitrary topological structure. Okay, so a very important fact, an expansion of the real ordered group, every constructible set is F sigma. So, okay, so if you have, say, you have a closed set and you consider the definable family of balls of some positive radius. So not in the Euclidean metric, but the some metric that's definable just with addition. But you consider these balls as r goes to 0. This is the family is definable, right? This is a bunch of open sets, definable, decreasing, and because C is closed, the intersection of all of these as r goes to 0 is C. So what do we get? The definable closed set is the intersection of the definable family of decreasing open sets. If you take the complement of everything, it just shows that an open set is F sigma, right?
Sorry, could we shut the door maybe?
Sure. The reason I'm explaining this is because this is the only reason that we need addition in this whole proof. To argue that because to construct this you need addition. If you just have the order, you can't. But it's because of this that we can argue, okay, constructible sets are F sigma. All right, so what more? So then we finally arrive at this proposition. Let R be an NTP2 expansion of the real ordered group, then every definable F sigma set is constructible. This is the main technical result and the real bridge between combinatorics and topology, right? So how do we prove this? I like to sketch the proof not for NTP2 but for NIP, although NTP2 is a bit more technical, but the ideas are similar, and it works like this. So let X be a definable, non-constructible F sigma set, and let N be an omega-1 saturated elementary extension. We identify X with its definition in the extension. X still has the same properties. X is still non-constructible and it's still F sigma, okay? Say that witnessed by some definable family curly C. Alright, so what do we do with this? So we're going to, well, first by lemma B, X is dense and co-dense in this type definable set K. Okay. And alright, we're going to witness the negation of NIP, the independence property, through sets of this form, through neighborhoods of some radius R around these sets in curly C. Okay? Alright, so again, we're going to go back to the pictures to try and argue this. How do you show this? So the independence property, this is, I apologize if you've never seen this, but I'm going to try my best to explain it just with words. So a structure has the independence property, meaning it's not NIP, if it defines a family of sets with the following property. For every n, you have to find n sets in that family, satisfying that every possible Boolean combination of these n sets that could, in theory, be non-empty is non-empty. So if you think about abstractly, like about the Venn diagram generated by these n sets, every area of the Venn diagram has to be non-empty. Okay? So, so again, this is a combinatorial definition, right? NIP means you want to avoid this kind of rich object. So in this proof here, we're going to construct something even stronger. It's not just this kind of family, but every area on the Venn diagram on every Boolean atom is going to contain a non-empty open set. Okay, so it's going to be a little bit stronger. So purple is going to mean an open set. Okay, so I'm going to sketch the proof up to n equals 3. Okay, so how do we do this? First, again, we are in this omega-1 elementary extension. We have our x. it's X is dense and co-dense in K.
Sorry, what's the statement you're proving again?
We want to construct this kind of object. We want to prove the independence property. So we started with X is F sigma and not constructible. And we want to show the negation of NIP.
Okay.
Okay, we tend to show in an NIP structure, every F sigma set is constructible. So we want to construct this kind of definable family from the assumptions which were X is F sigma, is dense and co-dense in K because it's not constructible, and that's it. Okay, and we're calling curly C the family that witnesses that it's F sigma. Okay, so how do we do this? First, because X is dense, you can just pick any point in X and in K, right? And then you pick a point C1 in curly C that contains this point. But because X is co-dense, you can also pick a point that is outside. And because C1 is closed, you really need that C1 is closed, you can pick a radius that is small enough to satisfy that not only Y1 is not contained in this neighborhood right here, but it's not even contained in its closure. Right? And now what we've obtained is these two open sets, right? One inside and one outside. The first step. Okay, so now back to the fact that X is dense. X is dense, so there's also in this second open set outside, there's also going to be a point that's in X. But then, you remember this notion of upward directed, right? So there's going to be a second closed set, C2, that contains both X1 and X2. But now you use the fact that X is co-dense. So again, in these two open sets, you have to be able to find points that are not in X. And now, once again, because C2 is closed, you pick a radius that is small enough to satisfy that set 1 and set 2 are not even in the closure of these open sets. And there you have it again. Our two open sets become 4. Yeah? And you continue like this. The whole idea here is, as long as C3 is large enough, but then R3 is small enough, you're going to be able to multiply by 2 the number of open sets. So this it looks a bit messy, but this, I promise you, are 3 sets and 8 Boolean atoms. All of them, they contain an open set. Yeah. You continue like this, and that's how you witness the independence property. Okay. All right, so that's a proof, and with that, proving theorem A becomes quite easy. So theorem A, the open core of every NTP2 expansion of the real ordered group is constructible. Okay, first of all, you only have to show that the projection of a constructible set is constructible, right? Because they are already closed under Boolean combinations. And the whole idea of the open core is that you start with constructible sets, right? But the thing is, okay, I'm going to tell you already that the projection of an F sigma set is F sigma. So proposition C is going to give us the theorem. So how do you do this? So first, X is F sigma, witnessed by a family curly C. But because we're in the reals, we may assume that the sets in curly C are compact. This is the reason we need some notion of compactness. Because your closed sets, you intersect them with like families of compact walls, and you can just make this assumption. But then the thing is, the family of projections, the projection of compact is compact, so witnesses that the projection of X is F sigma. And now you apply proposition C, and you get that the projection of X is constructible, and that's it.
In the case of NTP2, how could you generalize the argument? What formula you get to construct this kind of metrics? You said that you can generalize the idea of NIP to NTP2.
Right.
The last.
Which form? Okay. It's a bit more complicated, but the sets instead of being these ones, it's more like instead of being balls of this form, there are sets of this form as you need for NTP2. So it would be a bit more complicated. Whenever we pick one, then we pick countably many in a decreasing family, so that you leave an open set between them, and it still works. It's a bit more technical. It's not. The idea itself is not more complicated. Okay, so that's how you prove this, and now, well, first of all, when I used to give this talk a few months ago, and I used to say at this point, compactness feels like a trick. Like it doesn't. I didn't like it. It feels like having it for free somehow. This step here, and it felt like maybe NTP2 or some other combinatorial definition implies that the operation of a closed set is constructible. You know, something nice like that, and then you can argue theorem A for like in a way more general setting for NTP2 topological structures, right? But we do. The truth is, we do need something. Okay, and for that, I'm going to present the example here, which is the integers localized at 2. So these are rationals of the form P over Q, Q an odd number, and this is the p-minimal by work of Goodrick as an ordered group. Now, this is just ordered group language, so it's its own open core. And the thing is, this is not constructible. And in fact, what we get is the elements that are divisible by 2 in this group, they form a dense and codense set. Right? And the proof is pretty straightforward. So, this is a problem. You have the simplest of NTP2 or NIP structures, the p-minimal, and because it doesn't have any extra property, it doesn't have this kind of compactness behavior, then this proof doesn't work. And in fact, okay, what you have here is this closed set. Right, it's a closed set, but then its projection to the y-coordinate is not constructible. Okay, so you do need something. You might ask, okay, what if it was divisible? What if the group was divisible? What if we're in a field? Do we still need compactness? And this we don't know. However, let me make a few
Define
comments.
that last line. Why is A plus? Why is one of them in?
Why is this? Okay, so this is divisible by 2, but this is not.
Oh, okay. That's an assumption that Q and Q prime are.
Sorry, they are odd. Yeah.
What?
I should have.
They're not both. They're not odd.
Yeah. Q and Q prime are odd.
Oh, they are odd.
Yeah, of that form. So this is in divisible by 2. This is not. So then, if A is divisible by 2, this is here, and this is not. But if A is not divisible by 2, you can show that it's the opposite.
Wait, say it again. Q and Q prime are odd.
Yeah.
Okay, but then and A is what? A is any rational number, or what is A? What are A and B?
No. A is in this structure. In this structure.
Oh, A is there. Okay.
Yeah.
You mean two times Z localized at 2, or what? You say A plus 2 over Q is in.
Yeah.
So you mean 2 times that?
No. So the thing here is I'm picking two. I mean, this proof is quite schematic here, but I'm picking 2 elements in the structure.
Yeah.
And I'm trying to argue that this is dense and codense, this set right here. So I'm trying to argue that in between A and B, there are both elements that are divisible by 2 and elements that are not.
Okay,
Sure, but I'm with Bjorn. I mean, then in the last line, certainly the second formula in the last line.
You mean 2Z2, and then not in 2Z2.
Yeah, absolutely. Okay. Sorry. Yeah, you're right. 2C2, exactly. Yeah, thanks for taking that. All right. So, a few comments. This work suggests analyzing expansions of the real ordered group by closed sets under the following dichotomy. Either every F sigma set is constructible, meaning the whole thing is constructible, or there exists an F sigma non-constructible set, which we've shown it implies TP2. But okay, the obvious question is, can we get something worse? Can we get something even worse? And then the question becomes, in a combinatorial sense, what would be the worst that we can hope for? And with that, I'm going to go back to the paper I quoted at the very beginning. So Philip and Eric, they consider expansions of the real ordered group that define this two-sorted structure here, right? It's called the monadic second-order theory of the naturals with addition. And they say, and I quote, curly B obviously does not enjoy any Shelah type combinatorial tameness properties, NP or NTP2. Therefore, any structure that defines an isomorphic copy of curly B cannot satisfy any of those properties and has to be considered complicated or wild in this framework of combinatorial tameness. Alright, this is kind of like the worst case scenario. And then my question would be, instead of TP2, can you actually say, if there's a non-constructible F sigma set, you define an isomorphic copy of this structure curly B. That would be extremely nice result, I think. Like either your structure is as wild as possible in a combinatorial sense, or if not, then the open core is constructible. It would be a very nice, very strong dichotomy there. So that's the question. How it defines a non-constructible F sigma set that defines the structure even without addition, right? By one. What else can we ask? Well, there is this lifting question about constructibility. If R defines a non-constructible set, does it define a non-constructible subset of the real? So is it enough to check subset of R? Like we know this for the R definitions I gave before, noiseless and strongly noiseless, but we don't really know for constructibility. And the third one is, I said a few things about constructible topology. What more can be said? Are all constructible structures the minimal? Are already mentioned, right? And okay, with that, I want to end up a little bit with the big picture here. So say R expands, say the real field by constructible sets. As I mentioned before, if you define the integers, then you define the whole projective hierarchy, worst case scenario. If you're NTP2, you're constructible. My question here was, what happens here? I don't know anything about this region. Let me just talk briefly about this region here. Here there's a bunch of papers, one of them by Philip, where he introduces we call a Cantor set. So a compact set with no interior and no isolated points. Because it's a tame Cantor set, because it's not the usual one, it's not the ternary Cantor set. And he manages to show that this structure it doesn't define the whole projective hierarchy, and in fact, it's Borel. Every definable set is Borel. However, it's not constructible. The moment you have a Cantor set, even though it's compact, your structure, it stops being constructible. And that's everything. Thank you.
Questions? Sorry, go ahead.
Okay. Something different. A few slides back, you were saying that it seemed like compactness was necessary. If you're serious about wanting to know that sounds exactly like a reverse mathematics question. I mean, compactness is usually expressed as weak Königs's law. Mm-hmm. And saying it would be necessary for this theorem would essentially mean that over a weak subset of ZFC, if you assume the theorem, you can prove weak Königs's law, as well as vice versa, which is what we've already done. So if you want to go after that, I'm not an expert, but we can talk about it a little more. We can tell you what we want to do.
All right. Thank you. It's interesting.
Yeah, I wanted to ask, so in the case, you get anything stronger than constructible in the sense of kind of, do you know I mean, the question was whether you get all the way to the minimality, but did you get any kind of how the constructible sets should look like? Out of the proof?
Not really. I don't think there's much. I guess in terms of like understanding constructible sets more. I've been wondering more about, I think it's kind of awkward that we don't have examples that are between the minimal and constructible, which comes down to trying to prove that you define say a closed set with infinite Cantor-Van-Dixon rank, right? And something should exist there. But I haven't been able to advance much in that direction. But no, to answer your question, I don't know much more beyond constructibility.
All right, then let's thank Pablo again.